Hello everyone, and welcome to our presentation. My name is Puritan Spills, and I'm joined by Daisy Ren and Zealand Yoon. Josh and Wong also worked on this, and he sends his regards. Our advisors are Dr. Shanae Zhang, Dr. Song Hong, and Dr. Ramesh Malla. Today we'll be talking about wireless joint monitoring systems for safety of highway bridges. We will start a discussion with joint monitoring practices presented by Daisy. Then Zealand will discuss the sensor development, and then I will talk about the bridge deployment. On to you, Daisy.
Thank you, Pierre. So bridges are a major component in our infrastructure, and due to their multiple functionalities, they are constantly exposed to different types of loads and different environmental factors as well. Although bridges are designed to accommodate for some movement, excess movement can actually lead to deterioration of the structure. Expansion joints are designed to accommodate for some of this movement in the bridge, so one way to maintain the bridge is by monitoring the expansion joint itself. In this project, the goal is to develop a wireless sensor for expansion joint monitoring. In the process of doing so, initial literature reviews have been conducted to determine what current expansion joint monitorings exist and what the needs and demands for these systems are. After the initial research, a lot of international joint monitorings have been determined in China and Portugal. However, there is very little information on this topic in the US. This is critical because the United States lies in a region where the temperature and weather patterns fluctuate greatly, not just from coast to coast, but in regions such as New England, the temperature changes drastically from season to season. To further understand the current joint monitoring situation in the New England area, a survey was sent to 6 Department of Transportations in the region, which asked for further details about existing bridge material and time durations of bridge inspections. From this survey, we learned from the DOTs that 66% of the DOTs conduct biannual inspections, 17% conduct annual inspections, and 17% don't conduct unless condition ratings required to be done annually. In addition, we also learned that the DOTs are interested in long-term expansion monitoring, but the results show that roughly 50% do not engage in this practice because of limitations due to funding and resources. So the goal is to develop a wireless monitoring system that is both cost-effective and time-efficient. And using this information, we were able to go into the sensor development phase.
Okay, thank you, Daisy. For the sensor development, as shown in the figure 3, we have 3 components. The first is the reference sensors. We use the LVDT as the reference for distance measurement, and we use another GoV wireless sensor for the temperature and humidity reference. And for the remote node, we use an Arduino board to read the distance from the ultrasonic sensor. And we get the temperature and the humidity from the other sensors. For the ultrasonic sensor, the Arduino first triggers the transmission of ultrasonic wave, and then measures the propagation time of the wave, and then computes the distance. These results will be sent to CC2650 through the UART communication. And once the CC2650 receives the data, it packs the data into a data packet and transmits it to the 6-teach gateway. And here we use the 6-teach wireless standard since it supports the IPv6 for IoT devices. And it uses the teach mode from the IEEE 802.15.4 standard. This standard, the teach mode makes the wireless communication more stable with longer transmission distance. And after the gateway receives the packet, it will store the data into a local database, and also at the same time transmits it into a cloud-based database. And users connected to the local network can access the data through the user interface within the same local network. And here we use a portable Wi-Fi hotspot as the local network. And to deploy the sensors in the field and protect them not damaged by the environment, for long-time measurement, we use enclosures to cover the devices and the gateway to protect them, as shown in the figure 4.
Great. Now to move on to the bridge deployment, our goal here was to validate the performance of our sensors. So in order to do so, a 2-span steel girder bridge with a concrete deck has been selected. This bridge is located on 195 Talon Turnpike in Storrs Road, Connecticut. It crosses the Willimantic River and was built in 1959. This bridge's total length is 151.9 feet and has a maximum span length of 74.2 feet. For further information, this bridge is bridge ID number 1531. In this bridge, we see an asphaltic plug joint indicating that small movements should be expected in this bridge. In the deployment of our sensors, we deploy the ultrasonic sensor on the beam edge to measure the distance between the beam edge and the abutment wall. Due to thermal expansion, we expect this distance to change here. So, in deploying our sensors, we would like to validate the LVDT to the ultrasonic sensor, and we would like to validate our temperature and humidity sensor to the commercial temperature and humidity sensor. In figure 7, you see two charts. The first chart plots the temperature that is experienced during our deployment from the remote node and the reference sensors. Here we see that our sensors are in good alignment. And then in the lower graph of figure 7, we see the ultrasonic sensor and our reference sensor. Again, here we see good alignment, and we see a change of 0.3 inches. This shows promise for the deployment of our sensors in the future. For future deployments, now we can use just our remote node and leave the reference sensor behind to save power and initiate our long-term monitoring. At this point, I'd like to thank the TIDC for all their support and the GAN Fellowship and also the IDEA Grant for their support as well. Thank you so much for viewing our presentation, and please reach out if you have further questions. Thank you.